You can start.
Great, thank you very much for the introduction. So as the chair mentioned, I'm at MIT, and I'm also starting a group at the Université Paris-Saclay at the Institut Physique Théorique, and so I'm hiring a postdoc sometime in the near future, so if you know anyone who's interested, feel free to reach out. Great, okay. So how do I go backwards? Does this do it? Great, okay. So this talk is, can I take this? Okay, great. So this talk is structured as follows. I am going to have an introduction where I talk a little bit about sort of contrasting notions about what is topological versus what you would measure in a band structure versus what you might actually see. And then I'm going to focus on some phases of matter that have eluded aspects of different notions of topology and robustness, specifically focusing on topological crystalline insulators, which I'll explain. But essentially, they're topological phases that require additional symmetries. And then I'm going to show how, with some numerical and theoretical techniques, you can unveil properties of certain kinds of topological crystalline insulators that have eluded detection thus far. And just to summarize, the findings namely involve new kinds of anomalies, new kinds of bulk topological properties in the language of field theory, so different kinds of Axion angles, and anomalous surface states that carry sort of half the degrees of, or half for the topological properties of 2D topological insulators, and how this relates to 3D transport effects would be in the form of a new response effect, the spin-magnetoelectric response. So before I get started, it would be good to introduce my research team. So elements of this project started all the way back when I was a postdoc at Princeton, before COVID and all of this. So we had been thinking about this problem for a while, and so thankfully we found some time this year to put the paper up. So this is the first time I've given this talk where both papers are actually online. So the first paper was with Frank Schindler, then a graduate student in the group of Titus Neupert, now a postdoc at PCTS at Princeton, working with Andre Bernevig, among others. And Andre was my postdoc advisor when I was working on this. And then I have a new team working with the groups of Barry Bradlin at UIUC and Gregory Feet at Northeastern and MIT. And a lot of the numerics you see for that part of the project were done by Kwan-Sen Lin, Barry's graduate student, who is really excellent. I mean, if you look at the paper, it's a tremendous, tremendous amount of work. So Kwan-Sen really did an amazing job there. And we also had some DFT calculations done by Zijun Wang and Xiaopeng Guo at Institute of Physics in China. So to begin, why do we care about topological states? So I mean, we originally care because of quantum Hall states were unambiguous. They had a quantized Hall conductivity that you saw in an experiment, and you needed a theory to explain this extreme quantization of the Hall conductivity. And you didn't need bands to talk about this. So you could have some theories like this network model that didn't invoke perfect crystals or anything like that. And through people like Haldane, we now have models of topological phases that are very accessible. You can model them in tight binding, and if you add symmetry, you can find other topological phases and fancier invariants in the Chern number, and you can do DFT calculations and you can compute those invariants and say that I see a real material where I'm confident that the band ordering matches some symmetry-protected topological state. And so we have these two contrasting notions. We have something that's very, very unmissable in experiment, and then we have something that it has a really, really elegant theoretical description, but may not have a robust signature in experiment, or something obviously quantized. And to get at that point, you only need to look at something like a 2D TI to see that there's this sort of issue. So in the 2D TI, they have helical modes on the boundary if you compare them with a trivial state. But in terms of a bulk response, like a Hall conductivity, what was initially proposed was something like a spin Hall conductivity, because you have counterpropagating modes, and they have opposite Chern numbers. But the thing is, the spin Hall conductivity of 2D TIs is not quantized because spin-orbit coupling destroys the perfect spin sector labels. So one might ask, something about a 2D TI that is robust, aside from the helical modes on the boundary? Well, there is a signature of 2D TIs in the bulk. It's just very, very theoretical. So you can insert, if you have a model that has plaquettes, you can insert a pi flux into a unit cell that's shaped like a plaquette, and that pi flux will bind a doubly degenerate state, and that state acts as a spin charge separated soliton, and the fact that you get one of these per each pi flux is one bulk indicator of a 2D TI. I mean, it's not something exactly that you would do in an experiment, but in a numerical model, at least, it does count as a bulk signature of a Z2 TI. And the thing about 3D TIs, so moving up in dimension, that made all of this come together was that you have a description in terms of boundary states, but you also have a bulk description. So a 3D TI is a time reversal protected state. Its surfaces are gapless, and they have an odd number of twofold Dirac cones. And those Dirac cones are a condensed matter realization of what is known as the parity anomaly. I'll talk about this a bit later. But the parity anomaly basically says you can't have an odd number of symmetry stabilized twofold degenerate Dirac cones in purely two-dimensional systems. So the two-dimensional boundary of a 3D TI evades the parity anomaly. And you can, if you have an additional inversion symmetry or centrosymmetry, you can use the parity eigenvalues or inversion eigenvalues to determine if a model or a DFT calculation of a material is or is not a 3D TI. So you can compute a Z2 number from just inversion symmetry eigenvalues. So you don't have to compute some complicated loop invariant around the whole Broughton zone. And that makes it very easy to determine if something's a 3D TI. And so this was done in materials like bismuth antimonide and bismuth selenide. And then the Dirac cones were observed in angle resolved photo emission. And so the boundary state story is simple. But additionally, what we know about 3D TIs is they have a very clear-cut electromagnetic response that is quantized. So the response theory of 3D TIs is what is known as Axion electrodynamics. It's a modified form of regular Maxwell electrodynamics where you have additional magnetic monopoles. And essentially the thing that makes Axion electrodynamics different from regular electrodynamics is that you have this additional term, the Lagrangian. This goes as this E dot B term, where the proportionality constant is theta, or is related to theta, and theta is the Axion field. It's the Axion angle. It's defined modulo 2 pi, and it's odd under symmetries that flip E or B, but not E and B. So inversion or time reversal will do this. And so in a 3D TI, you have this picture where theta is pinned to pi, a non-trivial value in the bulk. And you take theta in the vacuum to be 0, and it's also known that Axion domain walls between regions where theta equals 0 and theta equals pi bind either half-Chern states or states that have odd numbers of Dirac cones. And the two are sort of related because of the role of a twofold Dirac fermion as a quantum Hall transition. And the thing about this theta angle and these half-Chern states is that they can be detected in experiment. And so, for example, with optical experiments, like the kind done by Liang Wu and Peter Armitage, and also this more recent Nature Physics paper, you can use things like Faraday and Kerr rotation to measure the magnetoelectric response, or infer the magnetoelectric response, and this coefficient of theta, or the coefficient of the E dot B term, up to, in the units of the fine structure constant, was measured and shown to be quantized. So we have this whole picture of 3D TIs where we know their boundary states and we know their response. And for that reason, we feel pretty good about their theory. We have good materials realization, so we can start to do experiments with 3D TIs and know what's going on. So for this reason, when you say things like, I want to see if a 3D TI is good for spintronics or something like current rectification, I have a strong theory base to fall back on, and I have a good list of materials. And so for this reason, if we want to integrate topological materials into devices in a meaningful way that captures something robust or interesting or enhanced about them, at the very least, we have to have a picture like what we have for 3D TIs, where we understand the theory completely at the level of lattice models, materials, but also at the level of response and field theory. So what other topological phases do we have? And so in 3D, in terms of gapped states, everything else, with time reversal symmetry at least, are non-magnetic systems. is some form of topological crystalline insulator. So this is a phase of matter that's protected not just by something that's a symmetry at every point in space, like time reversal, but also a spatial symmetry of some kind. So the first topological crystalline insulator proposed and observed through angular result photo emission was this tin telluride mirror, TCI. Also, there's some rotational component as well, if you want to get into the fancier aspects of the classification. But essentially, what does this have? It has Dirac cones on its surface, and it has more Dirac cones than a 3D TI. It has an even number, and it has two along lines of mirror symmetry in each surface Baron zone in terms of the classification. That'll help you get there. But there are many, many other kinds of TCIs. And in fact, there's some proofs, some very nice proofs from various groups that have shown that we feel pretty good that we know what all the non-interacting stable TCI states are. But what we don't know is, so, and because we were able to write down methods for enumerating all of these states, then we were also able to come up with ways based on the Foucault formula to efficiently screen DFT calculations, first principles calculations of real materials for these states using generalized Foucault formulas. And by doing this in a high throughput fashion, many groups, including my previous collaboration, found thousands of material candidates for TIs and TCIs. And we did this in magnetic systems as well, and the results are publicly available from our collaboration and from Chen Fang's collaboration. So our ones are available through the links below. But one issue that this revealed was that we actually have some great candidates for phases of matter that are topological, but in a topological crystalline sense, not in a 3D TI sense. And so we can even just focus on a subset of them. We can focus on the ones that are maybe called doubled TIs or topological crystalline insulators that are equivalent to 2 or 2 mod 4 copies of a 3D TI superposed. And these ones, on every surface that you would find, they have 2 plus 4n two-fold Dirac cones. But aside from surface transport, what else do they have? Well, because they're equal to 2 copies of a 3D TI, they have trivial Axion angles. So the theta equals 0 taken mod 2 pi. And it also should be noted that superposing is a very theoretical concept. So physically, this is just like inverting bands again at the same point in momentum space. So I'm not asking something ridiculous. Obviously, is there material candidates, but the physical mechanism is this double band inversion. And so of these, various states have been proposed that have stable fourfold Dirac cones or weakly split fourfold Dirac cones. But some of them, or at least all of these, cut into geometries that either don't preserve the surface symmetry, or even in some of the states, the ones protected just by inversion, all the surfaces you could cut and access are gapped. And domain walls between the gap states, some of the domain walls bind helical modes, and some people call these hinge modes because there is some picture involving actually taking the edges and thinking of them as a continuous transition between Miller indices. Now, as I said, there's been little progress on the response for TCIs, and so certainly we know that the hinge states are real. Materials, including those that have been floated as candidate higher order TIs, have 1D helical channels, and that is true. They have a Z2 nature. If I put them together, they gap out. If I put on magnetism, they gap out, and they have some ballistic supercurrent signatures. So they have ballistic supercurrent and some sawtooth stuff. So there's a story about bismuth that was very exciting for that reason. And elements of this were reproduced in WTE2. And so people feel like there are signatures of these 1D helical modes in things that are called higher order TIs, but there's several issues. First, while this picture about bismuth is very nice, bismuth is a semi-metal, has electron hole pockets, and some of the band inversion is quite narrow. And some other works have suggested that bismuth doesn't even have the right band ordering to be a higher order TI. It might be a weak TI, and that the hinge state pictures are something more from screw dislocations. But there's also theoretical issues with this hinge state picture. higher order topology, as it was invoked, is a very useful theory framework because it lets you classify all the models you could ever come up with at the level of Dirac theories, and then you can compare those to lattice models, and you can look at the different numbers of symmetry-stabilized Dirac cones and hinge modes, and you can find that there's things that have Dirac cones and helical hinge modes, but also things that have chiral hinge modes. So I could call these chiral higher order TIs, and I could call the other ones helical higher order TIs. But real materials don't have the kinds of perfect global symmetries that you need to have these hinge mode pictures have anything to do with the bulk topology. So, the thing about higher order topology as a theoretical framework is it only tells you about what's going on in the bulk if you have some perfectly cut flake or some perfectly cut nanorod. Even if I have a little bit of disorder on one surface or one surface isn't quite like the other one, then the hinge modes or the corner modes are no longer an indicator of anything going on in the bulk. They can entirely come from surface physics. So, first of all, bismuth doesn't look like this nanorod. I mean, even in the original paper, there's just one part of one surface has all these dips and divots and everything. And second, as I mentioned more theoretically, I can take a featureless, a trivial insulator, and I can glue lower dimensional states to it and reproduce the same configuration of 1D channels that one might call indicative or the hinge modes of a bulk higher order TI. So the hinge modes, unless you have perfect control over all the band ordering in the bulk and on all the surfaces, are not a signature in and of themselves of a bulk state of matter. And so what do we do about this? Well, what we found in this paper is that all the fermionic or spinful chiral higher order TIs, the things that have 1D or chiral hinge modes, can be classified as having a bulk theta equals pi term. So they're all generalized Axion insulators. And so for any of these chiral magnetic higher order TIs, you could break the symmetry that protects the hinge states, but just on the boundaries. So you imagine a very big sample, and you keep the symmetry in the bulk, like inversion, that pins theta to pi, and then you go through band inversion transitions on the surface alone, which is like gluing additional states to it, in a way that removes all the hinge modes. And then you could try to perform, at least theoretically, a magnetoelectric experiment where you put on a magnetic field and measure the polarization. And in this picture, you can theoretically at least tell the difference between this fully gapped sample of a higher order TI with a chiral higher order TI and a fully gapped sample of nothing. So the thing you're not allowed to do in higher topology is the thing you absolutely have to do to measure the magnetoelectric response. You have to remove the hinge channels because they would short out the charge that you accumulate on the surface to get the polarization. But for helical higher order TIs that have theta equals 0, and they have quantum Hall trivial surfaces because of time reversal symmetry, is there something like the axion angle theta that you could use to provide an indicator in terms of the bulk or the surfaces that something is going on that's non-trivial, and that may also be amenable to actual experiments. And so that's what we've been looking at. And so before I continue, I just want to ask, when do I have to stop for questions? But like what time? Very good. Okay. Thanks. All right, I'm going to take a quick water break then. Great. Okay. So, one way to probe a topological state is to look at some kind of defect. And so there's different kinds of defects. You can have disclinations. You can have dislocations. You can insert a flux tube into it and have the flux act as a kind of defect. And without getting too much into it, the answer to jump to the punchline is going to say that if we insert flux tubes into stable topological states like these TCIs, then we can get some signature that is a unique signature of the bulk. You can also, in some of them, get features from dislocations, and we worked out the whole story in this paper with Frank Schindler. But I'm going to focus on the response to magnetic flux insertion. And so as a warm-up, I already mentioned, but I'll revisit the 2D TI case, but even before that, in an isolated Chern insulator with an odd Chern number, if I say a Chern equals 1 insulator, if I have a model in which I have a meaning for inserting a pi flux, so my bonds are cut into ways where I can take a plaquette and I can change some of the bonds to make it have a Peierls phase, then what I find is that a pi flux in a Chern insulator binds a charge E/2, and you can kind of see that from the Hall conductivity. But for a 2D-TI, a pi flux binds a doubly degenerate state because it doesn't break time reversal. And this doubly degenerate state actually has unusual spin-charge relations. So this is recognized in these two works from Axion Vishwanath and Shucheng Zhang's group and Xiaolong Qi. So the point is these fluxons, when they're half-filled, they act as chargeless spin, and when they're fully filled, they act as spinless charge. And so the point is adding an electron actually makes them become neutral and spinful, and vice versa. So they have these reversed spin-charge relations, and they're the same spin-charge relations as the solitons in polyacetylene. So these are known as Heeger's reverse spin-charge relations going all the way back to the story from the 70s. And so we can leverage this to try to see if there's any features of a model of a high-order TI that has no hinges. So what I can do is I take a model. I'm going to start with a chiral high-order TI where I know already that the bulk has a theta term. And so I'm going to take chiral high-order TI. I'm going to put it on this hollow donut torus. It's a finite torus, basically. And I'm going to insert two pi flux tubes. Basically, it's periodic boundary conditions in the x and y direction and open in the z direction. And I'm going to insert two z-directed flux tubes. And I'm going to slowly crank up the flux to pi. And I'm going to keep perfect inversion symmetry in this geometry just for the purposes of detecting whether something topological is happening. Again, this is a numerical tool. I'm not saying that you need perfect inversion symmetry. In fact, I'm trying to say the opposite. So anyway, if I start with my entire model and diagonalize it, I find a big gap in the middle. And then if I crank up the flux to pi, I find that my entire spectrum has become topological in the sense that it has what is known as a filling anomaly. So this spectrum has two mid-gap states. And if I look at, if I don't count particle holes as symmetry, and I just count as inversion, I can deform the spectrum by dragging the two states up and down. But I can't change the fact that there's this either a missing state from the valence or conduction manifold, or that they'll have an imbalance. So this is known as a filling anomaly. It's a theoretical tool for diagnosing whether something with zero-dimensional states is topological in some symmetry-protected way. Again, not something you're going to do in an experiment. It is just the thing you're going to do to detect if something non-trivial is going on, which will then extrapolate to a response. So I'm just to separate this from papers that are saying I should make a giant flake of something and look on the corners and have a filling anomaly. So anyway, I induce a filling anomaly in the system by putting on a pi flux on two tubes. And if I figure out the localization of the two states, what I found is one state is localized on one end of one tube, and the other state, so it's a zero-dimensional state in 3 dimensions, and the other state is a zero-dimensional state on the other surface. And these each carry a charge E/2. So what did I find? I found that this top surface carries half of the pi flux response of an isolated Chern 1 insulator. For 2 pi flux tubes, I've bound just a single E/2 state. And the bottom surface similarly carries half the response of an isolated Chern 1 insulator. So the surfaces are half quantum Hall states, which is consistent with what is expected for theta equals pi. Additionally, if I just view, sorry, I'm having trouble with the laser pointer. If I just view the region between the two red flux tubes as one-dimensional system, like kind of a thick or a fattened SSH chain, then what has happened is the whole system has been given an induced non-trivial polarization by inserting the 2 pi flux. And that's consistent with the formula for the magnetoelectric effect. And so overall, just by doing this inversion symmetric pi flux, I have probed the surfaces as being anomalous and the bulk as having a response. So then let's see what happens if I double everything and make a helical high-order TI. Well, I find that all my state counting is doubled, which is what you'd expect from time reversal symmetry. So I have 4 mid-gap states. 2 are localized on one end of one flux tube, and 2 are localized on the other end of the other flux tube. Per surface, this is half the pi flux response of an isolated 2D TI. So this says that a helical high-order TI with no hinges still has a feature. It's that it carries half the flux response in this theoretical sense, of an isolated 2D TI. So the halves, the surfaces, are half 2D TI states. They're sort of time-reversed copies of the half quantum Hall states of an Axion insulator. They're not trivial or fully topological. They're anomalous. Furthermore, the region between the flux tubes looks like a thick time reversal doubled SSH chain in that it has spin charge separated solitons on its boundary. So by inserting 2 pi fluxes, I've induced a non-trivial time reversal polarization in the system, which is this doubling, or you can also call it a partial polarization. The polarization per half of the states is non-trivial in the sense defined by Fu and Kane in 1D back in this PRB in 2006. And so this is the first signature of helical higher TIs in the bulk and the surface that does not rely on hinges. It is an intrinsic bulk property and surface property in the same sense that the Axion angle is a bulk property of axionic TCIs and 3D TIs. So how do I make sense of this? Okay, so the first thing we know is that the surfaces of a higher order TI derive from a fourfold Dirac fermion. And for reasons elucidated in these papers, a fourfold Dirac fermion can be anomalous in the same sense as a twofold Dirac fermion if it lies at certain places in the Brouillon zone and you have symmetries like time reversal. So we know that there's some sense of fermion doubling for fourfold TIs that is analogous to the parity anomaly. Now, the K dot P theory of a helical higher order TI derives from a fourfold Dirac fermion, or an eightfold Dirac fermion, sorry. So an eightfold Dirac fermion admits a limit in terms of the gamma matrices you'd use where you don't have any spin texture at all. All the dispersion for 2 directions is just orbital. In 1 direction, it's related to just SZ. So I can actually make a model of one of these that has SZ as a good quantum number. And in this limit, then I can define theta per spin as if like the orbital character of the wave function is defining an axion angle, and then there's an orbital axion insulator with a spin up, and plus its time reverse copy. Now, of course, real materials, as I mentioned, do not have spin up symmetry. So the question is, in more realistic band structures and materials, how much of this picture survives quantitatively, this axion angle per time reversal sector, per spin sector? So we can define this by employing numerical tools. And so for my remaining time, which I may have eaten too much into, maybe I can do this in 10 minutes, I'm going to show some numerical tools that we implemented to validate this picture. So, I could do it analytically. I could write down something in terms of the Berry connection and compute it for the overall without spin sectors, and that's very complicated. We're going to do it soon-ish. But we have formulas in terms of hybrid Wanny representation and Wilson loops for computing the axion angle. And so if I could figure out some way of dividing the system in half, I could apply these numerical calculations to half of the states, and if I had some gauge invariant way, and I could extract this theta per spin, or this partial axion angle. And so does there exist a gauge invariant way of doing this? And the answer is yes. So Emile Prodan figured this out in 2D already. So let's revisit a 2D TI. So again, in a spin Hall insulator, I can define the spin Hall conductivity using the Chern number up minus the Chern number for the downspins. But with spin-orbital coupling, I don't have sector labels, so I can't define a Chern number that way, a spin Chern number. But I can compute something known as the PSP spin spectrum, which is a projector onto the occupied states weighted by spin. And this produces a gauge invariant spin spectrum where all of the states are pushed close to 1 or minus 1, depending on the expectation value of their. Oh, it's a matrix, but it's essentially the expectation value with them respect to spin. So I can basically shift the band structure into a new band structure, or map it in a gauge invariant way. And in this band structure, called the spin spectrum, I can compute the Chern numbers of isolated groupings of bands. And I can define a different kind of spin Chern number as the upper band Chern number minus the lower band Chern number. And the point is, when I have weak spin-orbit coupling, this provides the topological contribution to the bulk spin Chern number in 2D, or the bulk spin Hall effect. So I basically get a spin Hall conductivity that is roughly renormalized by the sides of what's called the spin gap, the gap that tells you how strong spin-orbit coupling was. And so it's essentially as if there's an emergent additional U1 symmetry, U1 spin in the system, as long as this gap is pretty big. So I can use the classification of U1 cross U1, as in like U1 charge and U1 spin, And so this gives me response coefficients beyond the Z2 invariant. So on the one sense, like I get very unlucky with my spin direction, spin-orbital coupling. I could be nowhere near this limit and just have a 2D TI. But if I'm close to one of these large spin gap limits, then I can also figure out whether I have like a spin Chern, an odd spin Chern, or no, like a spin Chern 6 state versus a spin Chern 2 state, even though both are 2D TIs. And so what we're going to do is we're going to compute the spin-resolved Wilson loops of a model of a helical high-order TI that was introduced in this work. And so what we're going to do is we're going to take this model. We have to add extra bands for numerical reasons. It's related to something known as fragile topology. Not worth getting into in this talk. Happy to explain, and it's explained in the paper. We are going to then, per spin sector band, if there's a spin gap, which there is in this model, we're going to compute the non-abelian Berry connection, the non-abelian Berry phase, the Wilson loop, and if the Wannier spectrum is split, which it is, we're going to compute additional Wilson loops. So you're going to compute the spin. There's basically 3 sets of bands, or 4 sets of bands. There's the energy bands, the spin bands, the Wilson loops, and the nested Wilson loops. So for each one, you have to create a projector onto some isolated set of bands, spectrally isolated, and then compute another spectrum and look at the winding of that spectrum. But the important point is that symmetries can be inherited by the spectrum if you design the projector to commute with a symmetry. So here, inversion symmetry is going to survive all the way down to the final Wilson loop. And that will allow us to determine whether the winding of that loop is an intrinsic topological property. And so what we find is that the nested Wilson loop overall has some helical winding. So it doesn't tell you, it tells you theta is 0 mod 2 pi. But indeed, per sector, the nested Wilson loops of each spin sector, even though I have spin-orbit coupling in this model, wind in such a way that's indicative of theta being pi. So this is numerical validation that I have this picture of a time reversal doubled Axion insulator with a 3D generalization of the partial polarization introduced by Fu and King. And that makes sense, again, because the Axion angle, the magnetoelectric polarizability, is the 3D generalization of the 1D polarization. So basically what we did was figure out some numerical technique for finding the time reversal and orbital doubled generalization of the time reversal polarization. And you can also compute the whether you have something non-trivial by computing a Chern number in position space. So essentially you can compute a Chern marker or a layer resolved Chern number in a slab model. And so for an Axion insulator or an axionic TCI, it's known that the layer resolved Chern number is going to oscillate in the bulk, but average to 0 in each unit cell, and only begin to have a non-zero summation on the boundary where it's going to saturate in a half integer value indicative of the anomalous half quantum Hall state. And this is a consequence of the surface parity anomaly. Again, odd numbers of twofold Dirac cones cannot be symmetry stabilized in 2D because of the parity anomaly. It's a hard boundary. But on the surface of a 3D TI, they are. And the reason that they can is because if you could stabilize them in 2D, you would be able to then gap them by breaking the symmetry and induce a half quantum Hall state without interactions. And the way around this is by just making the boundary of an Axion insulator, where you're allowed to have a half quantum Hall state without interactions because you have another half quantum Hall state on the other boundary to compensate everything. And so let's look what happens if we do this in a 3D helical higher order TI. So I make a slab, and we introduce or maybe modify, there's some existing similar things, there's some position space spin Chern numbers, but what we're going to compute is a layer resolved partial Chern number, where you project half the states into some sector where we have spin-orbit coupling, but not so much that it closes a spin gap in the position space for finite size calculation. And so if you compute the layer resolved partial Chern number, we find that even though the total Chern number vanishes in each layer from time reversal symmetry, the layer resolved partial Chern number saturates in a half on the boundary, indicating that the boundaries carry an odd integer spin Chern number, which is not allowed in an isolated lattice regularized 2D system. So this odd spin Chern number with time reversal symmetry is a new anomaly. It's a partial parity anomaly. And so in this paper that we had in 2018, and Chen Fang also had a paper with Liang Fu, the surfaces of TCIs were explained to be anomalous by looking at the constraints on band theory. And what this does, this kind of calculation in terms of partial axion angles and a partial parity anomaly, this provides some more insight in terms of the meaning of the fermion doubling in these papers from the perspective of spin orbital textures. And additionally, this is qualitatively different from a 3D quantum spin Hall state. So if I were to look at the layer spin churn, the contribution to the whole spin Hall conductivity of a finite sized slab of this, the bulk doesn't contribute because it sort of alternatingly vanishes like the Chern number of an Axion insulator, and I only get a contribution to spin Hall conductivity on the surfaces. So, the spin Hall conductivity is not quantized because of spin-orbital coupling, but this is still a spin-magnetoelectric effect. I have sort of half of a spin Hall response on one surface and an opposite half on another surface. So this is a 3D generalization of the spin Hall response in the same way that the axionic magnetoelectric effect is the 3D generalization of the Chern response, or the quantum Hall response. And it should be noted that in this field theory paper from Zhu and Wang, there is a mixed spin charge response like this that's related to bosonic SPTs in field theory. But to our knowledge, nobody's related it to sort of accessible materials and models, really non-interacting models and real materials in this sense before. So this is under, so I think I can wrap up in like 2 or 3 minutes and then take 1 or 2 minutes. Okay, so very briefly, this is understandable from the layer construction picture. And so what I really want to get at is to get at this, to access this state, you can introduce a new kind of layer construction, basically to assemble 3D states. And instead of the layers being Chern insulators or 2D TIs, what I do is I start with what is known as the spin space groups, the symmetries of space groups that have independent spin rotations. So I have all the crystal symmetries, and I start with, say, SZ symmetry, U1 spin. So instead of just having 2D TIs, I have quantum spin Hall states to construct my layer constructions. And then I can imagine adding spin-orbital coupling that is strong, but not so strong that it closes a spin gap. And then I can construct different states, like 3D quantum spin Hall insulators and time reversal doubled Axion insulators that have distinct spin-magnetoelectric responses and distinct Axion angles or topological invariants. And so that, this motivates a finer classification of insulators in terms of their responses, where you have to look at the gaps in different gauge invariant spectra, things like spin, but also valley and orbital, and they tell you about new kinds of non-quantized but enhanced responses. And there can also exist intermediate states, obviously, because I can close a spin gap without closing an energy gap. And in 3D, the spin gap closures are stable, they're Weyl-like. And so in a 3D TI, in fact, you have to have these spin gap closures, and that says the spin texture of 3D TIs is unremovable. And as a note, so this doubled strong TI limit of a helical higher order TI in this paper by Adrian Poe is in fact one of these spin-Weyl semimetals because it's just taking 2 copies of this and putting them on top of each other. So to wrap up, we applied this to real materials, including MOTE2, and we find that MOTE2 lies in this spin-Weyl semimetal regime. And if you put on a large Zeeman field, at least in the model, you can confirm that because you can convert these spin-Weyl points into real Weyl points, and you get surface Fermi arcs so you can measure in a surface Green's function. And so there's many things to do here, but the one that I really want to point out is, like the spin Hall effect was originally found and proposed in magnetic systems. So this spin magnetoelectric effect should have a magnetic, just an analog in a magnet, a 3D magnet. And so finding that, I think, would be one of the most interesting generalizations on top of the crystalline topological insulator story.
Okay. The seminar is open for the questions or comments. Yep.
Thank you for a nice talk. I had a question about the Axion angle. So if we consider a boundary obstructed topological higher order TI, and let's say the initial hinge states are helical, and after you add some kind of surface perturbation, you can make the helical states into a chiral state. Then would that affect the
into what states?
Into like maybe one was going up and one was going down, and then add a surface perturbation to give another dispersion. Would that affect the bulk Axion angle, or the spin resolved Axion angle?
So one of the major points of this is to do it in such a way that I don't ever have to invoke boundaries or anything boundary obstructed. So if I take that model and I make it periodic in all directions, you can compute this in the bulk And what you should hopefully see is that the gap in some operator, like a valley operator or sublattice, has closed. And if you keep that all the way preserved up to the boundary, then it tells you something about boundary transitions as well. But what this lets you do is quantitatively separate boundary dependent effects that are fully boundary dependent and the language of boundary obstruction, and things that are actually coming from the bulk. Even in something that's bulk trivial could have some other operator could have a non-trivial gap and some non-trivial invariant in this sense. And that gap could be large and quantitatively robust.
Okay, thank you for your answer.
Yeah.
Okay. Further questions, comments? I have a short question myself. So the effective theory, can you derive it from the fermions by integrating out the fermions and derive that? You showed that I can detect it. But
yeah,
I
mean,
curious,
so
like,
yeah, in the SZ limit, surely. And then also in this limit, I mean, probably in like a BF theory or like this limit, like the various things that give you a 2D that come from a 2D TI will appear with a half coefficient on the surface if you do that, depending on. So the short answer is yes.
but when you break the symmetry slightly?
When you break it slightly?
Yeah. Like you showed that the when the spin-orbit coupling is there, then the
Right. So in one of the questions is like in the low energy theory, how does the symmetry breaking manifest? And I think not all the. I mean, the point is that K.P theory usually stays symmetric in something where you break it at the lattice level, and that's one of the reasons probably why it's robust. I think breaking it all the way down to the lattice or the low energy theory level, I think, is a harder question. Yeah.
Okay, thanks. Other questions, comments? Yep.
Thank you for your good presentation. I have a question about the Chern insulator at the surface. How can it robust topologically exist?
How can a surface Chern insulator exist?
Yeah, so it seems, for example, top surface at Chern number +1 and bottom surface Chern number -1, then it seems they can be annihilated in the bulk.
Yeah, I mean, the whole point is they have to be connected to the bulk, like so that any measurement would give you an integer. I mean, it's a surface-dependent integer, but it's never a half. I mean, that being said, some of these optical things you're able to subtract out the other half, so people can potentially. I mean, this Nature of Physics paper claims that you really can access the half. Where is it? The Mogi one. But basically, the short answer is if you have a topological bulk, that's how you can get a half without fractionalization on the boundary, without interactions. And it's the same counting as Dirac cones. So, yeah.
Okay, thank you.
Okay, any question, comment? Okay, then let's thank the speaker giving very nice talk, and